Remember that probabilities always have to add up to 1. That's really actually all you need to remember to answer this first question from our last set of old exam questions. Let's look. A chance event can result in 3 future states of nature. So there's only 3 things that can happen. The first state, 2 states having a probability of 40% each. What is the probability of the third state of nature? This all has to add up to 1. So 1 minus the probability of the first thing happening minus the probability of the second thing happening. Right, well that must mean that whatever that third thing is, it's somewhat less likely. The probability is 20%. Okay, now speaking of probabilities, you must choose between 2 investments. The first investment will return $500 if market conditions are excellent, $250 if market conditions are good, $100, all right. You know what? I think I want to draw this because it's talking about an investment and a couple different things that could happen, and then it's talking about another investment in which different things could happen, and then it's asking me to test a series of statements about all of that. This particular question is much, much easier to answer if you organize it into a payoff table, because notice it's talking about 4 future states of nature, right? It might be excellent, market conditions might be good, and 2 different options or alternatives. Table. Much easier to look at this in terms of a table. Let's see the different things that could happen. Market conditions could be excellent. That would be nice. They could be good. They could be what? Fair. That's what's mentioned over here. Or they could be poor. And they don't mention anything else. Okay. Now, there are 2 different things to pick from here. They talk about the first, oh, there's 2 investments. You must choose between, oh, wait a minute, that first sentence was a giveaway. That's actually describing the decision. A decision is a set of alternatives. The first investment, the second investment. I'm not writing the word investment just because I'm lazy. This is all setting itself up to create a payoff matrix or a payoff table in which the rows are the alternatives. There's only 2, and the columns are the different futures that could happen. In this particular problem, there's only 4. Now, to populate the table, I can organize all this information that's quoted sentence style. Here's where you get $500. Here's where you get $250. If you go with the first investment and it turns out things are fair, you only get 10, and you get nothing if market conditions are poor. Now, the second investment will return $200 regardless of market conditions. That's what that looks like. All right, now, test the statements. If you are completely uncertain as to the likelihood of market conditions, that's this, 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 or this, you are unable to choose between these investments. That is false. If you're completely uncertain which of the market conditions are going to occur, that implies that you should give them equal weights, which is to say that you could compute the expected value of each of those 2 alternatives with a weight of 0.25 for excellent, 0.25 for good, 0.25 for fair, and 0.25 for poor, and then see who has the high. I mean, you could choose. It didn't ask you to do that, right? It is just testing if you know you can do that. So we say, nah, that's not true. I got a way. There are 5 future states of nature in this problem. 1, 2, 3, 4. No, there are not. There are only 4. So that's false. The expected value of the second investment is 200. Now you might think, oh, wait, but I'm not given any probabilities in order to complete the expected value calculation. Am I supposed to use the 0.25? Does 3 refer to 1 being completely uncertain? You're way overthinking this. It doesn't matter. Look at the second investment. Whether you think there's a 90% chance of the market conditions being excellent, or whether you think there's a 0% chance of the market conditions being excellent. I mean, it does not matter what probabilities you attach to excellent, good, fair, or poor. The second investment is going to return $200. That is automatically its expected value. Yes, we very much expect 200 from that one, so only the third one tests true. So that one was actually partial credit in its day. Let's look at this one. An ambulance generally transports from 1 to 10 patients a day. If the ambulance crew reports no particular pattern within that range, what is the expected value of the daily number of transports from the ambulance? This is a similar situation to this business up here about being completely uncertain, but just to stay focused, ambulance transports. Let me put that in front of me. They're saying there could be 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10 patients a day. They're saying any one of these things could happen. Okay. And they're saying there's no particular pattern. So what's the expected value? Well, you can do it algebra style and say, oh, well, that means the weight is 1/10 because there's 10 outcomes, and I'll say the weight times the outcome, and then I'll add them all up. Or we can remember that nice shortcut that if you're completely uncertain what's going to happen, thus you're using equal probabilities for each of the various outcomes, all you have to do is average them together. Average them. Now, so when you average, check me on this, when you average 1 through 10, that's where you get 5.5. You don't get 5. Okay. A component has a reliability of 75% and is backed up by a redundant component with the same probability. Which of the following is closest to their combined reliability? Oh, okay, so this question is about the reliability of a redundant set. There's 2 components, each of which are 75% reliable. Okay, what's the chance that this system is reliable, that the whole system, one or the other one, will work? Okay, so we need the formula for a reliability of a redundant set, although I like to just reason through it with logic. Reliability of redundant set. Well, let's see. It's 1 minus big bracket, little bracket, 1 minus R1 times 1 minus R2 times big bracket here. I'm just writing it out in the style of the book. Now wait a minute, what is this? This is the reliability of the first component. So 1 minus that is the probability that the first component fails. This is the reliability of the second component. So 1 minus this is the probability the second component fails. Multiplying them together is getting their joint probability, which is the probability of really bad luck. It's the probability of them both failing. But the system will only fail if they both fail. So 1 minus all of that, finishing out the formula, is the reliability of the system. Anyway, all we need to do is fill this out, because you go 1 minus, okay, big brackets, 1 minus 0.75 is the reliability of the first component, times 1 minus 0.75 is the reliability of the second component, or 1 minus 0.25 times 0.25, right, which is like what, 0.1 minus, oh, my calculator, 0.0625, which is, oh, okay, we're on the order of 94, right? 1 minus 0.06, 94% reliable. Okay, so each component in the set is 75% reliable, but pairing them up side by side, the net effect is that it's 94% reliable. Got it. Oh, now, conceptually speaking of redundancy and reliability, which of the following is true? Increasing redundancy increases reliability. That is true. Think about it. The more redundant elements you have, the less likely that you'll have a complete failure. 2, a crisis ends in an emergency. Let's think about this. Oh, right, because this last chapter has a lot of interesting keywords. A crisis is a period before a great change. If you are in crisis, you can see a problem coming, okay? And while you agonize about whose fault it is and who's going to do something about it, but it hasn't happened yet, we say that you're in crisis. Now, an emergency is something unexpected that you have to deal with. This has to be false. If you could see it coming, it can't be an emergency. It may be a very, very bad event, but it can't be an emergency if you can see it coming, which is to say you're in a crisis period. All right, so center one's false. Decreasing redundancy increases utilization. You know what? Unfortunately, I say that is true. Okay, so that means the top and the bottom test true, which means that would be partial credit. And then that would be partial credit. But why did I say, unfortunately, that that bottom one was true? Because this is usually why we drop redundant elements from the system, right? Because we like to be able to claim that we have very high utilization. And the more redundant elements you add, the more safety. But unfortunately, the overall use of the system's getting lower and your financials don't look as good. All right, so last question. Oh, another keywordy kind of question. The online order system for a pizza delivery service has just informed the Pizza Kitchen of an order for 333, it's an odd number, pizzas being delivered to a nearby residential address. Okay. The kitchen crew is surprised by the size of the order, but assumes that it must be the result of a very hungry customer who is hosting an unusually large party. The crew begins preparation of the 333 pizzas. This reaction, right, they are surprised, but they go ahead and they start on it, is best described as which of the following terms? Now, there's all terms there in one sense or another from the chapter. They got this order in online for 333 pizzas. Okay, they made a decision. Must be a really hungry person and have started to process the order, even though they were surprised by it. Okay, so first off, whatever is the correct answer here has to be something to do with decision making, like that part of the chapter, which means business impact. That I just kind of made up. And disruptive innovation, I mean, what's this got to do with innovation? It can't be that. Which does, in terms of keywords that are strongly about decision making, we're left with the 3. Now, wait a minute. First one, groupthink. Well, this is a group, and they did make a decision, so I don't know. But what actually is groupthink? Let's see if I can drag that on here without too much glare. Groupthink, a tendency to neglect full critical evaluation of a decision in favor of minimizing conflict within the group of decision makers. Now, this is a group that made decisions, but if it involved groupthink, there should be some element of they were afraid of upsetting somebody in the group if they decided differently. Like maybe the order number is wrong, and so that's why they went ahead and there's just, it's no information at all about the group itself and there being any conflict in the group. So I don't know how it could possibly turn out to be the best answer. We didn't have any information about conflict. Okay, so we're left with 2 other ones, and they're both intriguing. Outcome bias. Drag back the book. Outcome bias. Outcome bias. A tendency to assume a process is acceptable if its output is acceptable. Saying, well, they have gone ahead and gone with the 333 pieces. This kind of weakly describes it, maybe, in that I'm sure getting a sale for 333 pizzas is a acceptable outcome. And so they're assuming everything went okay because this was okay. I'm going to put a question mark here. I'm saying this is a weak descriptor, and actually it was partial credit in its day when it was on an exam. It's a weak descriptor. You say, well, why is it weak? Because who's to say that 333 is, I mean, that's not a very good description, that it's acceptable. They might think, oh gosh, we have to make 333 pizzas. This is totally not acceptable. I mean, we're assuming that they do want the cash. We don't really know. I mean, I'm only pointing out the weaknesses. I do sort of see the pattern. I'm just wondering if the one last choice that was left over is a better. Which of the following best describes their decision to go ahead and make 333 pizzas and attempt to collect on that? Normalization, what's that mean? A tendency to accept anomalies as normal events, particularly over time. Anomalies, they're surprised. That is a highly unusual number of pizzas to be ordered by a single address. That's an anomaly. They're surprised by it, but they shrug their shoulders, they normalize it. Must be a really hungry person who's throwing a really big party. They're taking something they know that doesn't look right, and they're changing it into something that, okay, that must have been right. They are making it normal. So, That is the best description to the kitchen crew's reaction to an order for 333 pizzas.